I'll be analyzing the motion of a ball that I threw, seen in this video right here. So basically what I did was I used my own height to measure this and so find out how many pixels there were, and then use the pixel to centimeter ratio to calculate this distance, which is the range, and also the distance between the point of release and the end point, as in the vertical distance. So this is my mathematical model for my projectile motion. Using distance over time, I was able to find the initial horizontal velocity as 3.576. Using the physics formula for displacement, I was able to find the initial vertical velocity as 5.875. Both of these are rounded off to 3 decimal points. Considering that acceleration due to gravity is minus 9.8 meters per second squared, y double dot, which is acceleration in the vertical direction, is minus 9.8. Integrating this and adding the initial vertical velocity, you get minus 9.8t plus 5.875. Integrating this once more and then adding the origin or the initial point of release, we get minus 4.9t squared plus 5.875t. Similarly, as we're not taking air resistance into account in this investigation, acceleration in the horizontal direction is 0, and therefore velocity in the horizontal direction will stay constant at 3.576, which was the initial horizontal velocity. Integrating this and adding the initial point of which is the origin, we find the horizontal displacement as 3.576t. So this is the acceleration graph in the vertical direction, which is minus 9.8, and as this is therefore a horizontal line, and it stays at minus 9.8 all throughout the motion of the projectile. In comparison, this is the velocity graph in the vertical direction, and we find that at 0, it is 5.875, which was our initial vertical velocity, and when vertical velocity is 0, time is 0.599. At the end of the motion, at t equals 1.44, vertical velocity is minus 8.2. So this is the vertical displacement of the projectile. As we took the origin as the starting point, at t equals 0, the displacement is also equal to 0. It reaches a max height at 0.599, which was also the same time that the vertical velocity was equal to 0. And then at t equals 1.44, the vertical displacement is minus 1.7, which was the initial displacement that I measured using the photo. If we analyze the horizontal motion now, horizontal acceleration is 0, and that means that all throughout the motion there is no acceleration in the horizontal direction applying onto the projectile. Similarly, the horizontal velocity stays at 3.576 all throughout the motion of the projectile. On the other hand, if we look at the displacement in the horizontal direction, it actually increases proportionally to the velocity in the horizontal direction as well. So at t equals 1.44, the horizontal displacement is found to be 5.149, which is actually the displacement that I measured using the video. These are the graphs obtained from video physics from the analysis of the motion of the ball. The top graph represents the horizontal displacement with respect to time, while the bottom represents horizontal velocity. Overall, the shapes of the graphs are similar to the ones generated by my models. However, variances in data can most probably be explained by error in making measurements and the ignorance of air resistance in my model that occurred in the actual motion of the ball. These next two graphs represent the vertical displacement on the top and the vertical velocity on the bottom. Again, the similarities between my model and these graphs can be seen in the shape, although the main differences are due to the lack of accuracy in the value of gravity and ignorance of the motion of the ball after the bounce, which the graphs have taken into account. Changing variables such as the acceleration due to gravity and including air resistance as part of the motion might allow the mathematical model to be more accurate and close to that of the analyzed motion. Thank you.